Okay, so let me just remind you where we in the story. So last time. I introduced this class of this parameterized function class called feed-forward ReLU neural networks. And remember, these are function classes which map a Euclidean space, which has domain and codomain in Euclidean space, and then it has these sort of intermediate Euclidean spaces that it's mapping through. And remember that these layer maps, these so-called layer maps, are of a very specific form. Namely, these layer maps look like some affine linear map with a component-wise activation function. And for the most of the time, my activation function so I defined this class, and I said that it had interesting geometry. And I also said that that I have discretization from this class. Is actually already part of it. So here we just replace this component-wise activation function, this piecewise linear function ReLU, with just this step function. And already this is powerful enough to represent any Boolean function. So our first illustration last time that feed-forward sign neural networks are powerful enough to represent that. And we proved it. Okay, so what I'm going to do, so I know that everybody is kind of eager to learn about transformers, and I'm going to hold off on that for a little while because I really want to dig into the geometry of this class of functions. And this class of functions is actually, you know, one big piece of the transformer architecture. And so what I'd like to do, and it will probably take me through the end of next week. So if you want to skip classes and then come back when I start talking about transformers, you know, probably you're safe to skip next week. But I hope you don't, because what I'd like to do is give another illustration of how discretization can actually tell you really strong information about the geometry topology of this class. So what I'm going to do through the end of next week, probably, or maybe I'll get done sooner, is give you a much less simple application of discretization, much richer application of discretization. So, so I'm gonna write something which you won't understand until I define. But for almost all, I'm going to measure theoretic sense. Any ReLU neural network. There exists actually quite beautiful algorithm. So you can program a computer to do it, and in fact, the person that created this algorithm has written programmed to it. that allows the extraction of homology groups. All homology groups. I guess over Z mod too. Successive decision regions and decision boundaries for binary classification tests. Algorithm from the discretization. So find the corresponding, just the data of the corresponding sign. Discretization is already enough to construct a chain complex that computes homology groups of decision regions and decision boundaries. Okay, so I need to tell you what a decision region and decision boundary is.
I have maybe a more basic question. When you say from the corresponding sign neural network, do you mean the function, the composite function of the network, or do you mean
the collection of data and how it fits together?
You mean
I'll say
okay, okay.
But you know, somehow all you need is the collection of data and how it fits together.
But by data, you mean parameters of
I
the?
mean the activation patterns that are in
Okay.
the sign neural network. I'll say precisely what I'm doing. I'm just trying to motivate what I'm going to do. So so warning, we have a lot of work to do before we can get there. But I promise that the work is worth it because the algorithm is quite beautiful. It's okay for me to say that the algorithm is beautiful. It's not my algorithm. It's really, really nice. All right, so let me just here's kind of an aside about decision functions because of the fact that we're in this math and ML program. I just want to highlight that decision problems are all over mathematics. Let me give you two examples that are kind of near and dear to my heart, just because I am not here. So, so decision problems are nothing more than binary classification. So you're given a collection of objects, you're thinking of them as being like the inputs, and you want to classify them as yes or no with regard to some question, some well-posed question. Okay, so here's some examples. Given a word, W, in a finitely presented group. So here's my favorite finitely presented group, the trade group. N strands. It has n-1 generators, and then two types of relations. One says that these generators commute if they're at least, their indices are at least 2 apart. And the other one says that if the indices are 1 apart, then they kind of satisfy this grade relation. This more interesting. So you might ask, given a braid word, is it the trivial braid? Does W represent the identity in the braid? There's an interesting example of a decision problem. Another interesting, probably more interesting example from the point of view of people in this building, or maybe even people that are part of the program but not yet in the building, given a knot diagram, maybe presented in some combinatorial fashion. So here's one of my favorite combinatorial ways of representing a knot. You connect the O's to the X's vertically and the X's to the O's horizontally, and you always go over the overstrand, the verticals always go over the horizontals, and you get a knot diagram. In this case, it's clear that it's the unknot. The diagram of the unknot, a diagram of the unknot. But you could ask, given a knot diagram, does it represent? I.e., is it isotopic to the sort of the standard circle, standard sort of embedding of the. So here are some interesting decision problems in mathematics. They're all over the place. And somehow if you're trying to do use an AI model or an ML model to solve a decision problem or to find an algorithm for a decision problem, first you need to represent your data in some Euclidean space typically. So if data has been represented in some way in Rn, so encoded in some way in Rn, so you've put in all your words, your great words, or you've put in all your knot diagrams somehow into some Euclidean space. Then what is the model going to do? Well, you're asking for the model to construct the knot from Rn. Plus or minus one. And plus one is going to be yes. And minus one is going to be no. And what that's going to do is color your Euclidean space into two colors. So maybe you'd say the red here or the yes or the nose. And then this boundary is where you're kind of unsure because it's in between. So the way that we model this typically with these parameterized function classes is that really we have some map from Rn to R, and then we take the sign function. And then we have plus one, minus one, and 0, and then F inverse of plus one with the yes region, inverse of minus one with the no region. So these are called the decision regions of the problem. And then F inverse of 0 is the decision boundary.
So maybe this is naive, but if we've defined F to go 2 plus or minus 1, I guess how are we understanding that the region, like the inverse image of 1 and -1 are going to be open, and so that boundaries are not included in either?
Yeah, it's a great question. So these maps are always continuous. And those will correspond to open sets. So, but you're hinting at something quite interesting, which is, I kind of assumed here that my decision boundary was dimension 1. That actually isn't always the case. Also, I should say, that actually typically the way ML people do these kinds of binary classification problems is not in a jittery way. Step functions are not great for learning. So, actually, usually what they do is they apply this with the sigmoid function. This was kind of the original activation function. And its graph looks like this, it looks like an S. You can see that as b goes to infinity, this goes to 1. If it goes to negative infinity, it goes to 0, and it's 1/2. So it's kind of, you're actually interpreting the output of this activation function on the final layer for a binary classification problem as the probability that the answer to the question is 1. Sorry, is yes.
When we view these decision boundaries, we normally thinking of the domain as all of Rn and not just the subset of Rn that our data set might receive.
Well, I see what you're saying. I mean, I guess yeah. So you're asking about what happens when your data set is actually much lower dimensional, your input space. I mean, I guess, yeah. Theoretically, this is what we mean, but, because we're probably assuming that we're sampling from a probability distribution that is whose density is nowhere 0, so it's possible to get up anywhere, but yeah, otherwise we just kind of take the intersection.
And so this function from Rn to R is just like the sign neural net without the last component-wise sign, is that right?
Yeah, actually, I'm thinking of this as being some parameterized function class that you'd use in an ML model. So this is not the sign neural network here.
Okay, this is
a
like coming from, okay.
But really, this setup works for any parameterized function class you might choose. But typically, the way that these problems are modeled is that you start with a parameterized function class that you're and you're trying to do regression on a parameterized function class, and then you cut off at some threshold, and you say everything above that threshold is assigned +1, and everything below is assigned. So somehow the regression problem that we were talking about before is the first step to doing.
If I were to be using a multi-layer model, then this sigmoid step would be
Only the last layer, yeah, right. So actually, this is something you see a lot, that if you construct a neural network model and you say it's a ReLU neural network, then you typically put the ReLU activation on the hidden layers. And then that last layer, the activation function, is kind of determined by what problem you're trying to solve. So if it's a binary classification problem, you use this logistic sigmoid and interpret the output as a probability that the answer to this yes/no question is yes. If it's a multi-class classification, there's something called softmax. That's what it's called. But yeah, none of that is particularly important right now. I'll tell you more about that later. But this is kind of a good thing to know, that the last layer map is often treated differently for these problems. So what I want to try to set up is to tell you how, if this function class, if you're doing some decision problem, and this function class is like a ReLU neural network class, that actually the homology groups of all the intermediary decision problems and boundaries. So I'll say what I mean by that in a second. Can be computed from just the corresponding sign neural network, the data. So. So what do I mean by these intermediary decision problems? Well, say that later, but let me say it now. This is the right moment. So you have this neural network with these hidden layers. Dimensional. And now, say you choose some neuron in one of the hidden layers. Well, you have this subnetwork that ends there. So you just take all of the maps up to here, and then you project onto that neuron. So I'll just say you can call ZL sub J projection reactivation. Output the J neuron in the L layer. Here, this is layer 2. And this is neuron 2. Layer. And then the second layer. And you can consider this subnetwork. And there's a decision problem associated to that as well, but by the same construction. Sign the J. The decision. Related to the L layer. Yeah.
Reactivation.
Oh, so.
Everything that comes, so that neuron is, when it's activated, that.
Yeah, once it's activated, you've applied whatever activation function you want to apply. And so if it's a ReLU network, you would have applied say the ReLU activation to it. But we want to just take it before you apply the activation and just be it signed, like we're doing here.
So that's not a neural network that's necessarily just has find outputs for each neuron. It has redo activations, but you're looking at the output neuron before the review. I'm just looking at it.
Yeah, I think I didn't make something clear before that typically typically when I talk about a ReLU neural network or any kind of neural network, typically we just don't put an activation function on that final layer so that we can do whatever we want. So when I defined a ReLU neural network before, I didn't put an activation function on that layer. Yeah, we're sort of imagining we really have a map from R into R. So this is what I mean by the intermediate decision regions. And the vision. So let me go back to this example that we drew from last time. Just a single layer neural network. Here's the neural network layer map from R2 to R3. And remember that these hyperplane arrange, these hyperplanes are just the zero sets of this, the output neurons. And also remember that these level sets are like the level sets of the dot product with this weight vector, this normal weight vector. And so we're co-orienting with this affine hyperplane arrangement in the direction that those dot products increase. And so in particular, we have let me not write down all the equations necessary. Instead, let me just remind you that this gives if we now imagine that we have applied sine, then we get colorings of all the points in R2 by these binary tuples. And write down all 7 of these. So what I want to describe here is that actually this gives a canonical base. You have a canonical polyhedral decomposition. Of the domain of this neural network. So what I mean by that is that you canonically, so given a parameter, here's the hyperplane arrangement associated to a particular parameter, you have a canonical polyhedral decomposition of the domain, which, and what I mean by that is that that you can realize the domain as the union of polyhedral sets. Of varying dimensions, and they fit together in a complex. So let me write down definitions. So we have them. Polyhedral set E is an intersection of finitely many closed affine linear half spaces. Or equivalently, it's the solution set of finitely many closed linear inequalities. And by the way, a bounded polyhedral set is called a poly. If we have now a hyperplane in Rn, be an affine hyperplane. Be a polyhedral set. H is said to cut P. If it separates P into two components. P has two connected components. Otherwise, H is said to support P.
Decision tree, not co-dimension one, in which case, how would we get polyhedral decomposition?
So we always get a canonical polyhedral decomposition, but the dimensions don't necessarily reflect the coding. So you're like touching on something that, that I'm gonna go into in some detail.
But is it always true that the boundary is really gonna be like the closure of F inverse of one minus its interior or something like that? They sort of, that makes sense. That is actually the boundary of F inverse of one and F inverse of negative one.
Right, so, so are you asking whether F inverse of 0 is always like the boundary of F inverse of topology? I think the answer is no. I think we'll have an example that should. Let me pitch, let me pitch it, but I will answer it at some point. Don't let me not. So I'm just gonna draw some pictures. Here's a polyhedral set, in fact, a polytope. Here's the case where H cuts. And here are some examples of H supporting. So, yeah, I'm still in definition mode.
You drew two H that actually like intersect P, but we'd also say it supports it if it just
Yeah.
doesn't. Okay.
Think so, yeah. Oh, maybe. No, I need the H intersect P is.
Okay.
Affine hyperplane or which. Yeah, actually.
Okay.
Would not be intersect. If it intersects it, but it doesn't cut it.
Okay. Supports.
So then here's another definition. The faces of P are the intersections of P with supporting hyperplanes. And the proper faces. And here's a not so hard exercise. Every phase of polyhedral set is itself a polyhedral set. point is that hyperplanes have associated to them the two linear inequalities that are naturally associated to hyperplane. So somehow this affine hyperplane arrangement also has associated to it a collection of polyhedral sets for all the choices of inequality, closed inequality that it could put on it.
So just to clarify on the definition for the faces, in the example you have for H that supports, both the side and the corner are faces, just a different coding.
Exactly, right. So, yeah, I should also say the dimension, so polyhedral sets can have various dimensions, so I should say that the dimension of a polyhedral set is the dimension of the affine hull. Where the affine hull is just the smallest dimensional affine linear space containing. This is like the geometry of, this is like geometric representations of linear inequalities and inequalities. That's what you are studying when you're studying polyhedral sets. Any more questions about? So in particular, here's my example of the two-dimensional polyhedral set. These are the three linear inequalities. This one, this one, this one, that's the intersection. And then the faces are all of these faces that you see. You can convince yourself that these are all intersections with supporting hyperplanes. The dimensions are exactly the dimensions you see. So this zero cell sits inside an affine linear space of dimension 0. A linear subspace of dimension 0. This one cell sits inside of this affine linear space of dimension 1. Okay. So they're all the definitions that we need. I just need to say one more thing. The definition of a polyhedral complex. C, dimension B. Is a finite set. of Polyhedral sets. Dimension. Through D, of dimensions up through D. Called the cells of C. And they just satisfy that you can form a chain complex. So one, if you have a polyhedral set in this complex, then all the faces are also in the complex. Two, whenever you have two cells in the complex, their intersection is also cell. Or is a mutual face. Example. Here's a polyhedral, here's a decomposition of R2 as a polyhedral complex with three, 2 cells, 3 1 cells, and 1 0 cell. But this is not. So this cell here intersects this cell. In a phase of P2, but this isn't a phase. So that was just a whirlwind definition thing, but really probably a polyhedral complex is what you think it is. It's just a collection of these polyhedral sets that has a phase structure. So it's appropriate for doing things like constructing chain complexes. So the first remark that I want to just write down, although I said it already, it's probably clear to you, associated to any hyperplane arrangement is a canonical, I guess I should say, any co-oriented. So in particular, if this hyperplane arrangement is realized as the 0 sets of some particular affine linear equations you've written down, then you have a co-orientation. So is a canonical polyhedral complex, which you can think of as a decomposition. It's a hyperplane arrangement in Rn. It's a canonical polyhedral decomposition of Rn. And cells are describable I should say, not necessarily uniquely. By a ternary labeling. So explicitly. So if you have these hyperplanes, so these are the these are the set of points which are the level sets for some affine linear equation. But you also have HI plus and HI minus, which are the corresponding closed inequalities. So in that picture, which I've erased. now label the cells. But again, not always uniquely. In this case, it happens to be unique. But if this is like H1. Three. Um, then not just these top dimensional polyhedral sets, but the lower dimensional polyhedral sets can also receive a natural labeling, which is just the signs of the outputs. Okay, so this one is plus 0, +1 +1 0, +1 +1 -1. And in fact, this 0 cell is well, yeah, 0 on 2 and 3, but 1 on. This is, so in particular, this chemical polyhedral complex, I'm just giving you an example for the moment. We'll more carefully define things next time if it seems like a good idea to carefully define things.
Might be not that much, but with your inconsistent, we change the filter.
Yeah, I guess that is true. So. I can't remember in the data of the hyperplane arrangement, you have an ordering of the hyperplanes, probably not, but yeah, maybe up to permutation of hyperplane.
I guess that, my question was on this, not necessarily unique. There are two things. You could mean, does a cell have a unique, only one label, or you could mean, does a label apply to only one cell? So
Right.
which is when you say not necessarily unique, are you referring to two different cells having the same label? Or a cell possibly having two different labels?
I mean that, a cell can have multiple labels. And I don't mean because of this permutation.
These don't just okay.
So, let me. no, can I come up with a little- So for example, imagine that we had two hyperplanes that were just right on top of each other. Actually, this cell is in a lot of different if you were gonna start trying to label the cells here, I mean, this is a polyhedral complex. But
If the hyperplanes were numbered,
Mm.
then it seems to me the label would simply be, you take a point there and you take its sign at each of the hyperplanes, and that seems, well, I mean, if they're, if they're co-oriented and numbered, yeah.
Function is well defined. What do I mean by non-unique? Maybe this is just.
So one thing, it's not obvious to me that you couldn't have two different cells that have the same label, but are. So I didn't know if that's why I didn't know if that's what you meant by it.
parts of the pool like, have the same weights.
we can move on if this isn't an important point.
Yeah.
Yeah.
It's not quite important yet,
Okay.
but I do want to, yeah, I do want to say exactly what I meant there. But for now, let's just kind of move on. So let me just recall something. Is that, which is that there is a generic situation. For hyperplane arrangements and for these canonical polyhedral complexes for hyperplane. So a hyperplane arrangement. And in fact, in a certain sense, this definition it helps us so that we don't have to worry about what's going on here. But let me just make a definition. Hyperplane arrangement collection of M hyperplanes Rn is said to be generic if every k-fold intersection has coordination is an affine linear subspace of Rn of coordination K. So a hyperplane arrangement, so remember this arrangement of hyperplanes is defined by some system of, a system of M affine linear equations and variables. And so saying that the arrangement is generic is saying that every k-fold subset of those affine linear equations has a solution set of the expected dimension. You expect when you intersect K, codimension 1 things to get something. And we'll call a ReLU neural network generic. If the hyperplane arrangement associated to each layer is generic. So this is kind of a natural thing to do from the point of view of wanting to say what the typical case is for these ReLU neural networks. So let me just. So you have this structure of these layer maps, and each one of them is an affine linear map. Affine linear map composed with some bona fide nonlinearity, in this case ReLU. But that affine linear map defines a hyperplane arrangement in each one of these spaces. So inside of here is the hyperplane arrangement associated with this growth layer map. etc. And in fact, each of these hyperplane arrangements also has one of these canonical polyhedral complexes associated to it. And the point is that, right, so as kind of a first pass at understanding what the typical case is for these, you might make this definition that you want these hyperplane arrangements to be generic. So in particular, this is an example of a generic hyperplane arrangement. But for example, if you have two hyperplanes that are parallel, then this is not generic. Because you want these two hyperplanes to intersect in an affine linear subspace of codimension 2, and they don't. And also, this is a question. So far I've described but not said precisely, but probably enough for you to kind of reconstruct the definition. This canonical polyhedral complex that you have in each of the layer maps, or sorry, in each of the layers. So for each layer map, you have a hyperplane, and you also have these plus and minus regions for each of the hyperplanes. And that gives you some picture that looks like this. And if the hyperplane arrangement is generic, then in particular, what you'll see is that the number of zeros corresponds to the codimension. So the number of zeros in the labeling for the cell corresponds to the codimension of the cell. So this gives a bunch of canonical polyhedral complexes for the layers. But actually what I really want to do is so what this is giving you is some kind of decomposition of each of these sort of elementary collection of decision problems, but only in this hidden layer. What I'd really like to do is kind of pull everything back to the domain, so that I'm really doing these decision problems in the domain.
At that point, then you're applying sign after every linear map, right? So you're now looking at sign.
So the cells of the polyhedral complexes are labeled by the sign. But really but the cells themselves are coming from the associated ReLU neural network. So here, to define this canonical polyhedral complex, we actually have the cells themselves. But the point is that the signs give us a lot of information. Or the point will be that the signs give us a lot of information. So here, when I define the canonical polyhedral complex, the data of the labelings, these ternary labelings of the cells, are coming from the associated sign. But the cells themselves are from the ReLU network. So, so now, so in the literature, you might see, people talk about bent hyperplane arrangements. And fold sets. So when people talk about bent hyperplane arrangements and fold sets, what they mean is the union of the decision boundaries for all of the intermediate. So this is the union over all layers. And neurons in the layer. Of the, so I define this pre-activation. Reactivation output of an intermediate neuron. So we're just looking at the 0 sets of those. And we're taking the union. So if you had a depth 1 neural network, it would just be a hyperplane arrangement, but it would just be the union of these hyperplanes. That's what people call the bent hyperplane arrangement for a depth 1 neural network. And for a deeper network, a thing that is not so hard to show is that each of these regions, on each of these regions, the map is linear, affine linear. And so when you start pulling back 0 sets from later layers, they'll be linear. Their intersections with these regions will be linear, but they'll bend as you. They'll be different linear. Subspaces as you pass the fold set for the previous layer.
So these are all pulled back to Rn0
Yeah. So this
via
is
the
in-
function, the FIs.
But in fact, what we're really going to want to do is pull back not just this, but the whole polyhedral complex. So. Say it again.
You mean not the whole polyhedral complex, not just this.
Yeah, not just the zeros. That we're going to want to label everything with +1s, -1s, and 0s. One for each non-input neuron. But I just wanted to, so I'm not going to actually, I haven't carefully defined any of this yet. But I want to point out that in the literature, people talk about bent hyperplane arrangements, and this is what they mean. It's the decision boundaries pulled back to the input layer. And what I want to point out is that it's a misnomer in the sense that, yes, most of the time it is a bent hyperplane arrangement, but not all the time. I mean, what you think of the bent hyperplane, not all the time. Let me just give a warning. So as defined like that. That hyperplane arrangement does not always look as expected. All parameters. Not even when the neural network is generic. So not even when all of the individual layer maps are generic. So let me just give an example so you can see what kind of things can go wrong. This is going to be a really simple ReLU neural network. What I'm going to do is So the affine linear map for this first layer is just the identity, no biases. So when I draw this, I just mean, so you're to see what the output of X is, you can take the product of this matrix with X and then join one. Okay, so this is the affine, this is the matrix for the affine linear map here. Here's first let's put 0 here. So it's a little bit confusing because so here's the first copy of R2. Here's the second copy of R2. And now so as you apply the identity map and then ReLU, anything that has a negative coordinate, that negative coordinate becomes 0. So you get pasted onto the non-negative orthant. And the reason I chose the identity is so it's kind of easy to see how it is. But basically this just gets the open subset here, well, actually the closed non-negative orthant here just maps to the non-negative orthant here. But this basically gets projected onto here. So the image looks like this. And this whole orthant here just maps to 0 because both coordinates are negative. So everything just gets pasted like this. And now, so here, let's think about what the hyperplane is for this layer map associated to this weight vector, weight and bias vector. And it's just, so here's 1, 1. So it's just the hyperplane that is orthogonal to this weight vector, but it passes through the origin. And now if you look at the 0 set and you pull it back here, you get everything. So this 0 set of this neuron is actually codimension 0. The pre-image of the 0 set of this hyperplane. So this is like the hyperplane associated to the second layer map. If you pull it back, you actually get so the bent hyperplane arrangement in this case doesn't look like a bent hyperplane arrangement. So for the first layer, the hyperplane arrangement is just the 2 axes. Like first hyperplane associated with the first layer. Second. Actually, this is and so this pre-image of 0 is actually not codimension 1. It's this whole cell. But you probably have the sense that this is not kind of the typical situation. In fact, if you choose instead a bias that is not 0, and you perturb your parameter. Replace 0 with something positive. And it will kind of be perturbed off of this sort of bad intersection here. And then it will be, and this, the preimage of this 0 set of this later neuron will just be empty. And if you turn it the other way, then all of a sudden, the pre-image here will be like this. And so in both of these cases, it does look like a bent hyperplanar matrix. And this is kind of a degenerate case. So what this is suggesting is that more is needed besides imposing that the hyperplane arrangements are generic in order to have our bent hyperplane arrangement and our canonical polyhedral complex be nice enough, or kind of what we're expecting. So maybe I'll just say to close. Describe the right typical situation. I mean, what we need is some notion of genericity, namely that, what you really want is that if you have K bent hyperplanes and they intersect in something. So what we need is this right typical situation. So what we need is transversal. And in fact, for the whole polyhedral complex. And once we have that, actually, just everything goes beautifully. We can actually start to compute homology of decision boundaries and decision regions completely algorithmically from the activation patterns. So maybe let me just stop there, and this is where I'll pick it up next time. And actually, it seems like I should be able to completely do everything. Finish this up. Thank you.